So we would like to prove the invariance under deformation retracts, where we first assume M to be a smooth manifold and sigma to be a submanifold of M. And so if sigma is a deformation retract, we can claim that the de Rham cohomology group of M and de Rham cohomology group of sigma are isomorphic. So since sigma is a submanifold of M, we can define the inclusion map and inclusion map of sigma to M, and we also can define a C1 family of smooth maps that satisfy the following three conditions. So to define sigma to be a deformation retract of M, we have to the psi have to satisfy the following three conditions, where when t equals to 0, it must be an identity map where mapping x for any x of M to x itself, and if t is equals to 1, the psi is a submersion map where it maps an x of M to sigma, and if for any t, if p lies on sigma, psi must map the point p to p itself. So psi t, in this case psi t would be an identity map of sigma. So initially we have the inclusion map. So the inclusion map would induce a pullback map of it induces a pullback map of the cotangent bundle of M to the cotangent bundle of sigma, and it also induces the pullback map of the de Rham cohomology group of M to the de Rham cohomology group of sigma. And from the above condition, we can see that psi 1 is actually a map from M to sigma. So this in turn it would also induce a pullback map of the de Rham cohomology group of sigma to the de Rham cohomology group of M. And the key idea to prove the invariance of under deformation retracts is to prove that psi 1 star and I star actually are inverses of each other between the de Rham cohomology group. So now we let omega to be a closed one form on M. So here we then can consider a scalar function where it is a map from the manifold M to R, and we can define it in terms of the integral of the closed one form itself, where psi is the curve defined previously, and it's a curve with parameter t joining psi 0 and psi 1, where t lies between 0 and 1. The key point here is to show that when the two pullback maps act on omega, where this I star will pull this omega 1 from M to sigma, and psi 1 would pull it back from sigma to M, and then we minus omega itself, it will equals to df. This will further implies that the equivalent class between omega and the equivalent class of omega that is pulled back. And so this in turn implies that psi t star is the identity map on the de Rham cohomology group of M. We now let a set of local coordinates, and so we can further express omega in terms of the local coordinates as the following. So now we assume that the whole curve of psi tx can be covered by only one local coordinate chart. But however, later we'll further generalize this case. So, and furthermore, we denote the notation of psi tix to be the ui coordinate of psi t. So now we go back to the definition of f earlier. So in terms of the local coordinates, we can further express it as the following. So if we further take the derivative of function x, we can have here. We will first have this expression for the integral. Now we would like to apply the chain rule in computing this differentiation. So now we apply the chain rule. Okay, and then since previously we defined omega to be a closed one form, we would have this following expression for any I or k. So if we apply this relation to this equation, we would have so we can rewrite this equation in this form by just swapping I and k for the first term of the integral. And now we notice that these two terms are actually chain rules, so we can further combine them. So now we have combined these two terms into just one, one partial omega partial t, and we notice that actually these two terms can also be further combined using the product rule. So we further combine these two terms into actually we can obtain a total partial derivative of t of these two terms, and then we finally can integrate this term out, and we can obtain the following expression. So we finally obtain this expression. And now, to prove the previous relation, which is this equation, we need to calculate, we need to do another computation where, so from the inclusion map that brings psi t to m at any time t, we then can define the pullback map. The pullback map, and we can compute it this way. This way, and then we further carry out the computation, which is trivial. Okay, so from this expression we can see that for any inclusion map that maps psi to m, and the pullback maps the pullback of omega, it will finally equals to this expression. And if we compare with the previous integral, which is this term, the previous integral, we can then further simplify it. So for the previous integral, we finally obtain this term, and then if we use this relation and substitute back, we can obtain since when t equals to 0, psi naught is just the identity map on M, and also I naught is also the identity map on M. So we have finally proved that this the two pullbacks, the pullback of omega on M to sigma, and sigma back to M, and if we minus back to of omega, actually equals to df, which represents that these two are of equivalent class, and hence the de Rham cohomology group of M and de Rham cohomology group of sigma are isomorphic. However, previously we have only assumed that psi t here it can be covered by a single coordinate chart. Now we now further generalize that there might be a finite many local coordinate charts that can cover it, as psi t is compact. So now we assume that we have a partition between 0 and 1, such that for each alpha psi t can be covered by only a single local coordinate chart. So if we use the definition of function x with finite many local coordinate charts, we can write down the following integral. We can write down this integral, since psi t in this case between t alpha minus 1 to alpha it's only covered by a single local coordinate chart. We can use the previous result that we obtain, and we can obtain the similar result, and performing the summation over n, we can get a similar result as before. So we can obtain a similar result as before, and this completes the proof of the invariance of deformation retract in the general case. To complete the proof of the theorem, we now further define an arbitrary one form on sigma, and we want to prove that the pullback map of the eta is equal to eta itself. So this psi 1 would pull this eta from sigma to M, and this induced inclusion map would then pull the one form back to sigma. So this is equivalently to the identity map of sigma. If we can prove this, then we can complete the proof of the deformation invariance of the deformation retract. So we first have a set of local coordinates on M, such that we can define a set of local coordinate system on sigma by using the immersion theorem. Okay, so now we compute the following. So we have this for the expression for the pullback of eta 1 form, and we continue the So if we apply the chain rule, we can have the following. So since we know that psi 1x is just the identity map for x on sigma, so in this case psi 1I is just the ui coordinate. So the I coordinate of psi 1 is just the ui coordinate, and so if we compute the partial derivative of psi 1I on uj, we will get a canonical delta function. So if we use this relation and we put back into this equation, we would then obtain so we'll then find that actually the pullback map of eta is just eta itself for any x on sigma, and since the pullback map, and in other words, we'll further have this this relation as due to the similar reason as before. So here we'll like to make a conclusion that we are able to get that the pullback map is equals to the two pullback is equals to identity map on the Deformation group of sigma, and then we have also proved that the inverse of the pullback map is also the identity map on the Deformation group of M. So since we can find that actually psi 1 and I actually are inverse of each other on the Deformation group, and so this completes the proof that the two are isomorphic to each other.